reference. So we have been using this like off-the-shelf model, and off-the-shelf by here means which is like a publicly available repository, and we trained it on the Mara dataset based on the annotations which were provided by Jared and corrected by Spencer. So this is an example of a YOLO image, and we want to sorry, yeah. So this is an example of an input image, and we want to over here, we want to detect like these number of shorts over here, especially like detect like locate them and count them, and like over here too. So how YOLO works over here is that it's you look only once. So it's literally look only once only. So it starts with by creating a grid on top of the whole image, and once it creates the grid, then it processes each block separately for one object detection, one object. And that means like here the grid, the each block size has to be at least like smaller than the whole object itself. So that's a limitation of the YOLO architecture. So this is like a example from the first version that came in 2015, and that was version 1. And then currently what we have shown results on, that is version 5. And right now in market, which is available, version number 8, latest one. So the base idea is same. They still creates a grid. There are just minor changes, like some changes in the way information is processed further on. So if there is like let's say a bigger object, there's a human being over here and this way and this way. So it will like make a detection on each, like a prediction on each block, whether that block belongs to the person, like the to the object, or it does not belong to the object. And then it creates like a kind of like clubs them together and create a bigger bounding box. So that's how YOLO works. In our case, what is it? So thing is, whenever we have a cluster, when you have a lot of animals together, so let's say like this is a like for example in this case this is a bigger block, and over here it can actually go like and find like one object or like multiple like objects to stack on top of each other, but like they can be only or like this is like bigger than this. So it actually when there is a cluster it tends to miss a lot of detections over there, and it does the and that means the counting is way off than the actual number too. So that is like the limitation of the YOLO model. So what we thought about is, so another option is you can actually increase the grid size. So like right now, this is like a 20 cross 20 grid that I drew on the image. So let's say if you draw like a much more denser grid, so that each tiny box in it is very small and can actually fit one single animal only. But then in the computation cost actually like grows exponentially, because then it is processing each of those pixels and like individually, and then you can have like large number of those. So there is a limitation with this model. So what we did is we built like a new approach. This is still work under development. We are still like working on it. We have some like initial proof of concept. So we took the input image, and most of the image, the time that we look at the like images, so they are like either all green or like all dry bushy area, and the animals are roaming around. They might be not clearly visible to us, but thing is wherever there is an animal on the background, the animal always have like a, though the color might be like slight similar, but the edges have like sharp boundary. So what we like did as like a prior, like a kind of a pre-processing, you can say, or like part of our new approach, we took like kind of like a frequency transform of it. And by that I mean is I like kind of gotten a list of the way all the intensity values changes around, let's say, the boundary of each animal. And so I took those. So in those cases, like where like the value changes, those are called as like high frequency. Like there's a very abrupt change. So those are like high frequency. And lower frequencies, for example, these greener areas. So there's like smooth green area. This is like almost irrelevant information. And this is noisy information too. So we want to kind of suppress that. So what we did is we took the frequency transform, and we like suppress all the lower frequency components. That means the greener regions, like which are there like very minimal changes. And then we see how what is actually looking in the image. And once we do, so the thing is like it actually like got rid of like almost 80% of the noise in the image, because all other sections were actually not relevant in the image. They are all gone, and it can actually like clearly highlighted, okay, these are the sections in the image you might want to look at. So for example, there's a cluster of sheep over here, the sheep over here. Even the paths which were there, they are kind of like occluded now. So I mean like those are suppressed too. And now we can actually pass this like more concentrated information to our like network. So we built a network to process this information. And so this one is like we take the input image, and then please ignore the like terminologies. These are just like jargons from the field. So, and then we process like do like kind of like an high pass filter, that is that blue image that we created at before, and then we do some information extraction from the color image that we see, and then cross attention basically means is whatever we saw in this highlighted region, we kind of like in very simple terms I can say is we overlay on top of the color image that we saw. So that means like it will just like mask out all other blue regions, like that is the mask, and then give attention, like focus to only the highlighted region. So we do that, and then we pass it to like a transformer, like and kind of like an encoding and decoding type of architecture, where we transformer is again like kind of like a terminology from the field, and this is evolved in natural languages, so it is derived from there into the vision field. So it's not relevant, but right now, so thing is like I want to say on this part is, so instead of like what Yolo was actually like looking on processing that single grid and then processing that to make like, I mean, find out like an object over there in that one, bigger one. So transformer, like we do is like, we do pixel, like we look at every single pixel in the image and try to identify what is its relation to the neighboring one, and if their cluster actually makes sense. If that is an individual pixel actually belong to something, or that is an individual object, or like bunch of pixels together. For example, a goat can have like let's say three or pixels. Like I mean, there could be like a uh, like up over here, like a pixel is means like actually like when you have the whole image, which is a bigger image of 1000 cross 1000. Like you have the image which is taken by your phone, that is 1024 cross 1024. So each like 1 cross 1 is called as pixel. So where that intensity values are stored. So what is like transformer actually is very good at processing every single pixel, and then its relation to all the nearest one, and also the farther away one. So, and then we do simple decoding of that process condensed information, and to try to locate, okay, this is where all the animals are. And basically, like, I mean, we process that information to actually find out boxes. Okay, these are the locations where the animals are. And at these locations, whether it was a goat, elephant, or what category of the animal is. So this is like the classification that is. So this is our like new approach. It is like almost there, but still under development. It's like not very well tested. So we are not sure like how well and where all it is going to perform well. But yeah. So any questions on this part?